So I'm going to make a video reviewing for the first exam this semester in 241, and just bear with me, this is going to be a really long video. I'm going to go through basically chapter 5 and look at the questions at the end of the sections and do a few of them, and the ones that I pick are going to be more likely to show up on the exam. So let's just see what we've got here. If you're looking at this on YouTube, you might want to maximize the video and also increase the video quality to HD, which you can do by fiddling with that little sprocket looking icon in the bottom of the screen. So let's just look at a few of these. Which one looks good? I hate these picture things. Estimate the area under the graph of cosine. This is pretty good. So number 3 is pretty typical. So let's do these, number 3, and let me switch this thing to graph paper. And so we're going to look at cosine. I can draw a little picture here. So there's the y-axis, and there's the x-axis, and let's draw some cosines. So cosine from 0 to pi over 2. So that's going to be from 1 down to cosine of pi over 2 is going to be 0. So here's y equals cosine. And we're supposed to estimate this area. I realize now that I should have drawn it much bigger, but maybe I can just zoom in. Okay, let me zoom in again. Alright, and we want to approximate it with 4 rectangles. It's too bad I didn't draw it better, because it would be nice if the 4 rectangles corresponded to the graph paper, but don't worry about that. In fact, so it's not distracting, I'm just going to turn that off. So let's make some rectangles, and let me make them in red. So first we're supposed to, whether you're going to use the right endpoints or the left endpoints, either way you want to divide the domain into 4 parts, because it says using 4 approximating rectangles. So 1 part, 2 parts, 3 parts, 4 parts. Okay, and this thing will help me draw some straight lines, hopefully. Let's do the right endpoint rule first. So up, up, help me. Okay, that didn't work. Up. Okay, good. Good. All right. And this right endpoint has 0 height. So this is a rectangle of height 0. This is a rectangle. This is a rectangle. And that's a rectangle. Okay, so you don't really need to do the picture to do this problem. You could work it all out symbolically, but this kind of helps us figure out what's going on, and I guess I'm doing a little review of how everything works. So you know the common width that all these things have, that's called delta x, and the formula for delta x is that it's equal to b minus a over n, and n in this case is 4, b in this case is pi over 2. I'm going to make that a little bit smaller. Okay, sorry. B in this case is pi over 2, a is 0. And so that means that delta x is equal to pi over 8. And I'm also going to need the xi's, so there are going to be 4 of them in this case. x0 is always a, so it's just 0. And x1 is delta x, and x2 is going to be 2 delta x's, and x3 is going to be 3 delta x's, and x4 is going to be the same thing as b, which is pi over 2. Okay, and now I can write out the Riemann sum. So it's going to be, the general form is that it's delta x times f of, since this is the right-hand rule, you start at 1. If it were the left-hand rule, you would start at 0. So this is the general formula. In our case, this is pi over 8 times cosine pi over 8 plus cosine pi over 4 plus cosine 3 pi over 8 plus cosine pi over 2. And I'm not really sure what cosine of pi over 8 is. I guess you could use a half angle formula or something, but let's just use a calculator. Feeling a little bit lazy. So let me open up this calculator called Speed Crunch. Sure. So here we want to do pi over 8 times cosine pi over 8 plus cosine, maybe I should have just done this dumb thing in the calculator in the first place, pi over 4 plus cosine 3 times pi over 8 plus cosine, this thing better be set in degrees or I'm going to have a freak out, pi over 2, which we don't really need the calculator for. And just because I'm feeling a little paranoid, let me make sure, yeah, it's in radians, so that's good. So let's see what that's equal to. So that's equal to this number. And so that's the answer. I'm not going to bother to write that down on the paper here. So you can see that it is 0.7907. And I guess I will write that down. So this is equal to 0.7907. And it might be interesting to compare that to the actual answer, which is from 0 to pi over 2 of cosine x. Which is actually equal to 1. And the reason I know that it's equal to 1 is because I have memorized that, you know, 1 lobe is worth 2, and this is half of 1, so half of 2 is 1. So the true answer here is 1, and we're getting an underestimate. So we can do this same problem again, doing the left-hand rule. So part B here is we're supposed to do it using the left endpoints. We just did it using the right. So let me undo all that, and then we'll just do it using the left. Okay. So let me fix up the curve a little bit. So, you know, the difference in the picture is that now the left endpoints are determining the heights of the rectangles. That's kind of pathetic. Let me turn my helper back on. And so since the left endpoint is determining the height, it is going to go like this. Oh, so sad. So come on down like that. And here's the left endpoint determining the height again. And since this is a decreasing function on this interval, what we're getting now is an overestimate. The math is really similar. You know, the difference between, this is for the right-hand rule. If I were going to change this to the left-hand rule, the difference is really minor. In fact, let me just cut this and paste it. The only difference is, instead of starting at 1, now we start at 0, and instead of stopping at n, now we stop at n minus 1. And so what that changes down here, what that changes in the formula, so now this is for the left-hand rule, is this is all okay. We don't count the last one anymore because that is the nth one, which we are throwing out. and we have to add the 0th one. So we have to add cosine of 0. So I'll just say, cosine of 0 plus all this other stuff. And there's that also has a really minor effect on what happened here in the calculator. So can I get this back somehow? Come on, dumb thing. Okay, it almost cooperated with me. So I've got this stuff back here, and an easy way to do both at the same time is just to change this to a 0, which of course has a value of 1. Now I get this number 1.1834. Okay. 1.1834. Now this is an overestimate that I get from using the left-hand rule, and this is the underestimate that I get from using the right-hand rule. And that's it. So that's just a really easy Riemann sum question. So let's see what other kinds of questions we have here. These are going to be kind of boring, I think. So this one is good because number 15, it has to do with one of the most important facts about calculus, which is that calculus gives the relationship between location and velocity. So very important for physics and for using calculus for real life. If you ever use calculus for anything, it will probably be related to the derivative of location being velocity and the integral of velocity being location. And number 15 here is emphasizing that connection. It says the velocity graph of a braking car is shown, and you can see that little decreasing red line there. Use it to estimate the distance traveled by the car while the brakes are applied. And let's actually do that. That's not too hard, and I like it because it has a meaning, and we want to practice using the meaning. So use it to estimate the distance traveled by the car while the brakes are applied. So it's just going to be the area under the velocity curve, and that's because of the Net Change Theorem. And I'm not going to state that, but you might want to Google it. You can always pause this video. I'm just a recording, so feel free to pause it and check on it later. This says that basically that the integral of the rate is the amount. So from A to B of the rate gives the amount of B minus the amount at A. So you should understand what that means. If you don't, then you need to read about the Net Change Theorem. Okay. So we're going to use that here. We are looking at the area under the velocity curve. The velocity is the rate at which location changes. So if we integrate velocity as a rate, we'll get an amount, which is the net change in location. And that's exactly what the problem is asking for, is the distance traveled. That is, in other words, the net change in location. So we're going from 0 to 6 of the velocity function, whatever that is, dt. And the true answer would be, the location at time 6 minus the location at time 0. And this is the elapsed distance, or the distance traveled, which is exactly what the question is asking about. But they don't give us an expression for velocity. We're supposed to just use this, and that's where Riemann sums come in. And there are many correct answers. Probably the smartest thing to do would be to use the midpoint rule, and it's also kind of a nice review of the midpoint rule, so I am going to do it like that. So first let's figure out, if we're going to use Riemann sums, what delta x is going to be. And by this graph paper, I guess that should be dt instead of dx. They're suggesting that for dt we use 1. So that's because, see how they're going over by 1 each time? So let's do that. And then I'm going to pick midpoints to determine the heights of the rectangles. But I can't draw on this PDF, so I'm not going to draw the rectangles. So the midpoint of the first subinterval seems to be at a height of about 3/4 of the way between there. So that's like 3/4 of 20. So that's about 40 plus 15 is 55. So I'll use 55. So we'll do 55 plus, now this next one seems to be close enough to 40, so I'll use 40. And this next one, if I go up the midpoint here, it seems to be about 30, so I'll use 30. And this one seems to go up to a little bit less than 20. I'm going to use 18. And this one is 10. I'll use 10. And for the very last one, looks like it's about a quarter, or what would you say, like maybe an eighth of 20. I don't really want to divide 20 by 8, so I'll divide 20 by 5 and call it 4. So it's approximately this. If you added up all these numbers, that gives the distance traveled by the car while the brakes are being applied. So I've been kind of cagey about the language. You know, this is net change and distance. So why should net change be the same as the distance traveled? It would definitely be true if there were absolute value signs on this thing. Because if you put the absolute value signs on, then it's not net change anymore, it's just the absolute distance traveled, and that's really what we're interested in. And the reason why this is already the total distance traveled is because in this problem, on this interval, the velocity function is positive anyway, and so adding the absolute value signs wouldn't change anything. This is the right answer. So let's do maybe one or two more from this section. So, you know what? I guess I'm actually kind of bored of this section. What about number 20 and 21? These are good questions. Determine a region whose area is equal to the given limit. Can you do that? Let's do number 20. So we're looking at the limit as n goes to infinity of the sum as I goes from 1 to n of, okay, so I could write some stuff here, but let me write it out abstractly. So I want to think of this as f of xi delta x, and I sort of want to recover what those things might be here. And so there are probably several right answers. It looks to me like one thing you could do is make delta x equal 2 over n. And xi here, you can think of xi as a plus I times delta x. So is there some way, maybe we can think a here is 5. That would make sense, and actually I times 2 over n makes perfect sense for what we already have for delta x. See how this is consistent with what we already picked for delta x, so that looks good. And so as a function, it is x to the 10th power, because that's the function that's being applied to xi. And as far as a and b are concerned, it would make sense if oh, so we already know actually that a is equal to 5. So b, since delta x is also equal to b minus a over n, b minus a needs to be 2, and if a is 5, that means b needs to be 7. And so we could say that the region whose area is equal to the given limit, this is from 5 to 7 of x to the 10 dx with, do we need to say anything more? No, it's that's it. So this would actually be equal to that limit by the definition of the definite integral. And you should ask yourself, do I know the definition of the definite integral? What are those words that Hunter is saying, what do they signify? It's my duty to know that, and if I'm slightly unsure of what he's talking about, because he's a little bit crazy, so maybe he's just not making any sense, but if he is talking about something, maybe I should look back through the chapter and try to find that definition so that I know that definition too. So that's what you're thinking. That's good. And now I really am sick of this section, so I'm gonna pause the video and go to the next section. Okay, so here we have the questions for 5.2. So let's look through here and see if any of these look good. So what about this? Evaluate the Riemann sum with 6 subintervals. Yeah, I'm sick of that. You need to be able to do that. I'm just tired of it. We've already done it. Also, this basement is kind of hot, and I think I need some water. Here, the graph of a function is given. Express the area under the curve from 0 to 8 using, yeah, no thanks. You do need to do that. It's just that I feel like we've already done it with that long Riemann sum problem before, so I'm skipping that. This is also a Riemann sum problem. You need to know how to do all these. These are really easy. They're so easy and so boring that I can't even stand to look at them. Use the midpoint rule with the given value of n to approximate the integral. Yeah, you need to be able to do it. Maybe but it's so boring. Do I have to? Use a calculator or a computer to make a table of values of the right Riemann sums with n equals 5, 10, 50, or 100. So that sounds kind of fun. What value do these numbers appear to be approaching? Find an approximation. Oh my god, these are all about Riemann sums. Riemann sums, Riemann sums, Riemann sums. Seems like all they've done is introduce the definition of the definite integral, which I guess maybe is all that they did do. Okay, so how about number 33? Number 33 I can actually stand to work on. And just because I said those other problems were bad and boring, that doesn't mean that you don't need to know how to do those things. They're just really tedious, really simple calculations that are a lot like that Riemann sum problem that we've already done. Now, number 33 is asking about the meaning of the definite integral interpreted as an area. So let's answer the question A here. So it's asking about the area under this curve that they've given you here between 0 and 2. So it's just counting squares. So you can see that I have 3 full squares here, and then half a square and half a square. That makes a total of 4 squares. So the answer to A is 4, and that's because each square is 1 by 1. So the answer to part A is 4. Let's do B. So the answer, they want the area from 0 to 5. So I'm just going to remember that we already have 4 here if I can, and just count the rest. So how many is that? I've got 3 full ones here, right? 1, 2, 3, I think you'll agree. Now look at this block of 6. It goes 1, 2, 3, I shouldn't have touched it. 1, 2, 3, 4, 5, 6. It's getting cut exactly in half. So that means this part is equal to 3. So I've got 3 plus 3 is 6. Okay. So I already had 4, and I've got 6 more. So that's the answer to B. I think I'll set this thing so it's always on top. Probably I'm going to regret that. So let's look at C, and C is from 7 to 5. Or sorry, from 5 to 7. So from 5 to 7 is going to be, it's half of these 6, so that's 3, so it's negative 3. And part D is from 0 to 9. So actually the only part that I don't know is this little part from 7 to 9. So from 7 to 9 is 1, 2, 3, 4, 5. So that's negative 5. So what have we got? We've got minus 5, and that's between 7 and 9. And we've got negative 3, and that's between 5 and 7. Okay. And from 0 to 5, that's the positive part. That's what we got as an answer for B, so that's equal to 10. So the final answer for D is 10 minus 5 minus 3 equals 2. So that's the answer to D. All right, and let's see if we can stand to do number 34. Use the graph of G. Oh, the graph of G consists of two straight lines in a semicircle. Use it to evaluate each integral. Well, that's a pretty good question. So let's just start with number 34A here. By the way, if you're just watching me do these, it's not going to help you learn as much as pausing the video, doing it yourself, and then checking your answers with mine would do. So I strongly suggest you do it that way. In fact, it would be absolutely tragic if you're just sitting there watching me solve these problems. That's a very bad idea. That's one reason I hate reviews and I hate tutoring. In fact, I even hate doing the problems for you in class, because you can't learn to play the banjo by watching somebody else play the banjo. That's why I spend so much time in class trying to get you to do the problems. The only way, I'm poking the microphone here, the only way you are going to learn how to do these problems is by doing these problems. So if you're watching this video hoping for a miracle, it's not going to work that way. You have to try to do the problems. I'm just giving you the answers. And I'm also doing this because people will like it. People tend to like these review videos, but that your intuition that makes you want to review a video like this is actually wrong. You should turn off this video immediately and just do all these problems yourself. It would be like 1,000 times better for you. But anyway, number A is, let's see. So we want the area from 0 to 2, and this is just block counting again, so it's just 4, right? Because it's half of these 8 blocks. And let's do B. And from 2 to 6, so here's 2, 3, 4, 5, 6. So it's just that semicircle. So that's 1/2 pi r squared for that semicircle, and it's going to be negative because it's beneath the x-axis. And it looks like the radius of this circle is 1, 2, so this is going to be minus 1/2 pi times 2 squared, and so it's minus 2 pi. And for C, what is it? From 0 to 7. So it's going to be the sum of these first two, 4 minus 2 pi, plus this extra little bit between 6 and 7, which is 1/2. So if you want to call this 4.5 minus 2 pi, you would be exactly right. Okay, so let's see what else they got here. Okay, so this is a good thing to be able to do. These are also good questions here. Number 35, let's say. So you have to be able to graph a function, and I guess I'm in kind of a bad mood. I've already walked like 10 miles today, and I've got low blood sugar, and like I said, it's hot down here. And it just puts me in the mood to lecture an imaginary person who I can't even see, but I feel frustrated because I feel like a lot of people can't make these graphs. And it's okay if you can't. It's not like I'm mad at you because you can't graph it or anything. I know. I probably could not have done it at your age either, but think how hard people have tried to teach you to graph a line like this. You have to take, like algebra in high school, then you take college algebra, then you take pre-calculus, What do you learn in every single one of those classes? It's how to graph a damn line, right? So if you still can't do it, it takes 5 minutes of your time if you concentrate seriously to learn how to do it. So do it. So the y-intercept of this line that I'm talking about is the line given by the equation y equals 1/2 x minus 1, and minus 1 is giving me the intercept, and the thing that makes this 0 is x equals 2. So that gives me the entire line if I just connect these 2 points, like so. And now it's asking me about the area between 0 and 3. So let me put 3 here, turn off the ruler. Right. So you can see that there's a little bit of positive area here. Right. And there's a little bit more negative area here. So I'm going to think of these as being 2 triangles, a pink triangle and a blue triangle. The pink triangle is going to count negatively, and the blue triangle is going to count positively. And what are the thing that makes all this possible is the formula for the area of a triangle, which is 1/2 base times height. For this triangle, the base is 2 and the height is 1. For this triangle, the base is 1 and the height is f of 3, whatever that is. So that is 3/2 minus 1, which is 1/2. So this height here is 1/2. This is a triangle with base 1 and height 1/2. So what have we got? We're going to count this one negatively, we said. So that's negative 1/2 base times height. That's 1/2 of 2, which is 1. And we have to add it to this. 1/2 base times height is 1/4. And so the answer is minus 3/4. So that's the answer to 35. And the way you do, say, number 37 and number 36 also is you have to be able to recognize the formula for the upper half of a circle. And this is another thing that frustrates me. I know I don't teach the same students every semester, but sometimes it feels like I do. And it can be like you're just talking to one really thick-headed person for years who just never understands what you're saying. But the formula for the upper semicircle is the square root of r squared minus x squared, where r squared is the radius. And that's being used in problems 36 and 37 here. This radius is going to be 2, this radius is going to be 3. And that's how you can solve these problems. You can't do them, quote-unquote, analytically by taking the antiderivatives. Those antiderivatives are too hard for us right now. And if you try to find the antiderivative, you'll either, if you think you've done it, you've made a mistake. So you can't. And what you can do, though, is draw a picture. Actually, this is a pretty good picture for number 36. For number 36, all we have to do is make r equal 2. And this is going to be minus 2, this is going to be 2. And the answer for number 36 is going to be 1/2 pi r squared, which is 4, so it's 2 pi. That's the answer to number 36. For number 37, the picture is going to be slightly different, but similar. Let's see if I can push that stuff up. Oh, can't do that. Do I have to open up another page? Okay. So for number 37, let's see. Okay, so it recognized that as a circle. So number 37, they're not quite asking you about the graph of a circle, are they? Because it's had 1 added to it. So that means this whole circle thing is going to be pushed up by 1. And this circle's radius is supposed to be 3. So in my diagram here, this is 3 and this is 1. And what this is asking you is, how much area is there from, this is going to be the origin. So this is the origin. And they're asking you about this area basically to the left of 0 and over to -3, which is right here. Sorry, I can't write with the ruler on. Here's -3, so just, it's all this stuff. So how much is that? That is, that's just this box. This box has dimensions 3 by 1, right? So the box has area 3. And this is 1/4, the circular part is 1/4 of a circle of radius 3. So how much is that? That's 1/4 pi r squared, where the radius is 3. So that's it. So the final answer is 3 plus 1/4 pi times 9. And that's a great answer for number 37. For these questions involving the absolute value of x, you know, the absolute value of x looks like this big V. And you can figure out these answers by using triangles. For number 39, it's really clear. It's just, you know, here's -1. And you get this triangle. So because this line is y equals -x, you know that this is just 1. So you've got a 1 by 1 triangle there, and it's positive, and then you also have to take into account this triangle from 0 to 2, and so that means the base of this triangle is 2, and the height is also 2. So you add these two regions together, and that gives you the area. This is similar, except the, you know, because people have been trying to teach you how transformations of functions affect the shape of their graph for like 6 years of your life. I know that's an exaggeration. I know, like, maybe you don't know, but I know that very few people in the class can actually do this. And having spent a year teaching 141, trying to get them to know it, it can be very frustrating when nobody in the class actually does. So if you don't understand how transformations of functions affect the shapes of their graph, that's something that you might want to look into, and it's all explained in chapter 1 of the textbook. So what else have we got here? Use property 8 to estimate the value of the integral. Oh yeah, let's not do that. I hate property 8. I just remembered what it is. So what about number 47 is very important. Can you do that? Let's just get a new page here. So number 47 says, write as a single integral in the form a to b f of x dx. So let me show you. Notice that they don't tell you what f is, and I didn't make a super big deal out of this in class, so it's one reason I want to do it now. Alright, so we need to, they don't tell us what f is, so we just have to use our imaginations. And sort of, turn the ruler off. Sort of imagine it just, you know, doing whatever, just kind of generic function action. And it looks like the lowest number they consider is -2, and the biggest number they consider is +5. And what are they doing here? They're looking at this first integral that they consider. I have to put 0 here somewhere in my diagram. 1, 0. So let's say that this is 0. And that means this is 1, 2, let's say. So they're considering this area. Okay. So I'm just going to kind of hash this. Right? And that's what they're calling the integral from -2 to 2 of f of x. And now they're going to add the area from 2 to 5, and I'll call that this red area here. Okay. And now they're going to take away the area between -1 and -2, from -2 to -1. So let me shade that. Here's -1 in the diagram. So they're taking this area away. So the magenta lines and the blue lines cancel each other out in that region, and that basically just annihilates this. So you can see what's left, the region that we're actually going to count, is just the area under the curve between -1 and 5 of f of x dx. And that's the answer to number 47. Very important thing to understand. Number 49 you should be able to do, but I'm not going to do it because I'm just not. Number 67 is a good exercise, but it's not of central importance. So I wish I hadn't done that. Now I can really get sued by James Stewart. So I'm going to pause this. Maybe I should just stop it because all this has gone on pretty long, and I'll just make a part 2 later. So I'll see you later. I'll see you in what for you might be a few minutes and what for me might be a little bit longer than that.